Hello, everyone. Welcome back to Unit 2 of Physics. And we were talking about one dimensional kinematics, or the motion of objects in one dimension. So, starting off from where we left yesterday, well, let's recap a couple of things. What we did yesterday, the first thing we discussed was distance versus displacement. And we went over what the definitions were. Distance is the total space between 2 points or measurable space between 2 points. And then the displacement was the shortest measurable space between 2 points. Um, and then we talked about, well, that the important distinction between these two is again that distance is a scalar property, so only got a magnitude, whereas displacement's got it's a vector quantity and it's got both a magnitude and a direction. The other thing that we went over was the other thing that we went over was frames of reference. And frame of reference essentially allows you to locate or pinpoint the location of um, an object that you're looking for based on the example that you did yesterday. So that's the location of your computer in your room um, from three different corners. That's one thing. So you were your hands were the frame or the you were the frame of reference with you being the center or the origin, right? And then you're measuring from your location where the computer was located, right? So that's frame of reference. Now we went through this little example where we went over basically that if I were to look at the University of Dayton to the distances or displacement of CJ from there, that's this yellow line. Um, how can I locate it? Well, if I draw an origin here where I'm standing by this server point, um, what happens is that there's this yellow line which is locating, and then there's this green line which is locating the position of University of Dayton. So the yellow one is the location of CJ, and that distance right here that you see, this yellow line, is the displacement from that origin point to CJ, whereas this green line is the displacement from this origin point, or where that everything is zero, star and goes to University of Dayton. The yellow line, on the other hand, was the displacement between CJ and UD. Um, and it, like I said yesterday, it remains the same no matter where this reference frame is going to be located. So if I were to move this entire thing and move it over to St. Anthony's Church or the Emerson Academy, this displacement between UD and CJ would remain the same. The displacement of UD and CJ, depending on where this frame of reference is located, is then going to change. But the displacement between the University of Dayton and CJ is not going to change. So that's what we went over yesterday. Now today we're going to talk about velocity. Um, so velocity. Well, we had introduced the concept of speed before, and speed was basically distance divided by time, if you remember correctly, or if you remember. Um, and then velocity, it only differs by the entire thing with the fact that you're replacing distance by displacement. Now, the difference between distance and displacement, that carries forward, right? So speed, since you're measuring total distance, travel divided by total time taken. This is a scalar quantity, so it's only going to have a magnitude. So speed is a scalar quantity in turn, and it's only got a magnitude. Velocity, however, is the total displacement divided by total time. So that is going to be, since this is a vector quantity, and this is going to be another vector quantity as well, right? So that's what we were talking about. It's a very simple definition. However, there are a lot more there's a lot more going on underneath or beneath the surface in this case. um, there's a formula associated with this, and average velocity here is going to be whatever your final displacement is, subtract the initial displacement for it from it, and then whatever the total time was taken. So the final time and initial time. So F and I are subscripts that are going there. So your total velocity average here is the total displacement divided by the total time taken to cover that displacement. Right, so moving back to, and well, trying to apply and differentiate between these two, let's go back to the original example that we've been discussing for the past couple of weeks, which is my journey to school from UD, right? So UD, I work at Kettering Labs. So moving from Kettering Labs, there are three different route options that Google Maps gave me. And they are 2.2 miles, 2.1 miles, and 2.5 miles, depending on which street I drive on, right? Um, and then I've populated this table. So if I take route number one, which is 2.2 miles, it's going to take 8 minutes. My average speed here is going to be 2.75, right, into 10 raised to power negative 1, just note this down, miles per minute. Now, this is another way of writing it down. So I'm using the scientific notation here. My answer is up to 2 decimal points, and I'm using the scientific notation here because the actual answer, if you were to, because 2.2 is smaller than 8, my answer cannot be, larger than 2.2 here. But essentially, make a mental note of this, take a mental note of this, that I'm writing it differently. And it's one way to write what your answer is going to be. So if I take route one, which is the South Main Street one, it is going to take me about 8 minutes to cover 2.2 miles, or my average speed is going to be 0.275 miles per minute. If I take the Brown Street one, which is 2.1 miles, it's going to take me 8 minutes. My average speed is going to be 0.263 miles per minute, right? So remember when I said that it's got a lot more traffic signals on it. So that's the reason why it's taking me um, longer to cover a shorter distance compared to route number one. And then if I were to take the South Patterson Street, um, again, it's 2.2 miles, but it's going to take me longer as well. And that's going to be, my average speed is going to drop down to 0.244 miles per minute, right? So um, this is the speed. Notice because I'm looking at the total distance that I'm traveling. However, if I go back to, well, this picture here, which is talking about displacement, I'm sorry, Google Earth does not show this as displacement, but this is actually displacement because it's not looking at the actual route that I have to take. So the image on the right shows the displacement, which is 1.22 miles. Um, so if I were to, again, measure whichever the table I showed you previously, for the distance I've traveled, this varies, but the displacement does not. So the displacement stays constant. The time, however, changes given on the distance that I'm traveling. So my average speed here is varying, and so is my average velocity, which is, in this case, displacement divided by the time. So my average velocity for route 1 or route 2 remains the same. However, for route 3, it's going to be lower, and it's 0.136 miles per minute. And all we're using here is the same formula that we used before. So it's the total, so the end of the position, so right here, CJ, and the start of the position, and that's 1.22 miles, and the time taken depending on the route that I took, right? Because I can't really travel this displacement. Um, so the time is going to not change whichever sort of between the distance or the displacement, but my average velocities and speeds are going to vary. And the formula that we're using is the one that I showed you before and a couple of slides before. Um, so we can take this thing a step further. And what we have is, let's start working on an example. So this is an example from the book, the whole physics book. And what we've got here is that there's a runner who takes about 55 seconds to finish a 400-meter race, right? The start position is at 0 meters, and the finish position, XF, is located at 400 meters. Um, and then the position of the runner is tracked after every 11 seconds, right? So that's one thing that we're working with. So what I can do then is I can, given this thing, I can map out this data, and this data has been provided. So it's being tracked after every 11 seconds. So that gives us 5 intervals. So zero starting position, 11 seconds. That's where the first position is noted. And the runner was at 60 meters, then 22 seconds, and the runner was at 135 meters. 33 seconds, that was 220 meters. And now at 44 seconds, the runner was at 315. And finally, at 55 seconds, the runner finished the race of 400 meters. Now, one thing that I can do with this data is I can plot it, right? So when I've plotted this data, what I've done is I've taken this as a scatter plot. Now, this shows me what's going on. Now, clearly from this little data here, the data snapshot, what I can tell you straight ahead that this is not a straight line. Why? Because the distance covered between equal time spots is not the same, right? You've got between the first 11 seconds, you've got 60 meters, and for the next 11 seconds, you've got 60 and 15, so 75 meters, and then so on and so forth. But the important thing that I can do here is that I can actually show you this in another way. So this is our original data, and this is the line that's going through it, right? So through those 6 scatter points that I showed you before. But if I were to go from the start to the finish point, it would be a straight line. So this straight line that has just popped up, um, that is going to show you that what our uh, curve would look like, or graph would look like, if the runner was covering equal distance, or covering equal distance and equal time spots, or um, time intervals. So I decided to do one thing, and that was to do with show you how you can work with the data that I'd shown you in the slide before on the Google Sheet. And there are some students who are having problem with trying to um, plot all the data and the different plots that are there. And there is another important tool that I want to show you within Google Sheets that you will probably need for the example at the end of today's lecture. So right here, what you see here are the different timestamps. So 0, 11, 22, 33 to 55 seconds. And then we've got the distance that was measured between in meters, and the different distance that was covered um, between the different timestamps. So one thing that I can do is that I can go click insert here, right, and can directly insert a chart. And what that does is this chart is started. Let me resize this. So I can, this chart is inserted right here, and you can select a different chart type here. Now there's this line plot, there is this area plot. I usually like to work with scatter plot because it's easier to do. So what I can do now is I can select my data range. In my data range, what I can do is I don't need this. This is not right. So I can do my distance, right? Because that's my dependent variable, and time is my independent variable, because this will keep on moving and this wouldn't be affected by anything else. This is affected, and this is the one that I'm measuring. So let's hit OK. And that's what it plotted at, but there's no x-axis data. So let's click on and on the x-axis, click on select range, and then just highlight that range, right? And it should do it for you. So now what you're seeing is that there's this time on the x-axis and there's distance on the y-axis. Now you can basically go ahead and do a line plot or the area chart, which we'll talk about later some other time. But let's start working back with the scatter plot. And what I was trying to get to is there's a very important tool embedded into any spreadsheet software that you're going to use, and that's to do with a trend line. So if I click on these data plots, right, what has popped up now is you see that there's an option to insert trend line. Now, different softwares have different methods to insert a trend line, but since you've got access to Google Sheets, let's stick with what this option is. So you've got trend line insertion tool here. So what this has done is this has inserted a trend line. And now this is a linear trend line, so for it will try to fit a straight line which best fits or all the points that you have placed around here. So all these data points that are closest to this line, and it's going to modify this line to best fit these data points. What I can do now is I can do a polynomial fit, or hang on, let's go back to linear fit and let me do this. Let me do a label and use an equation. Now what this equation is telling you is this is the equation for this line that's best fitting data points, and it's a linear equation because it's a linear relationship, right? For every increase or decrease in x, the value will change accordingly, right? And if I do a r square value, r square is basically a fit statistic. The closer it is to 1, the closer it is able to predict these values or the actual values, right? Um, and then what you can do is I can change it to a polynomial fit. And what you see here is that this equation is changed. So there's a constant, then there is a multiple of x. Now x here denotes to the x-axis and x squared. And the r square value has increased to 0.999, which you can assume that it's almost equal to 1. And this is a much better fit than the one that I showed you beforehand. Right, so these are a few things that you can do to essentially get to a better fit. Let's try to see if I change this value. So polynomial degree means the degree or this x value. So let's go to 3, go to r square, and r square is changed to 1. So this is a much better fit, and it's saying that it's going to accurately predict where these data points are going to lie if you were going to use this equation. So, and then what you can do with this equation then is basically substitute in for, let's say, the time. So using any value of x right here. So if I were to ask you what was the position of the runner at 15 seconds, you just need to plug into this equation a value of 15 and solve it, and it would return to you a location where the runner was at any given timestamp. So for 15 seconds, it would be, let's say, around, it should give you an answer for around about 97 meters. Now, I haven't done this, but you can do that. So that's a very powerful tool embedded into all the spreadsheet solvers, as I like to call them. Coming back to the original presentation, what we were talking about, so that was one thing that I wanted to talk about. That was the equation tools. But what you see here is that we plotted a line fit, and we'd done this little line which was going to show you that if the runner was covering equal amount of distance and the time intervals, the line would look differently. But how can you determine the velocity from this plot, right, or from the position time plot, which this is? And that the way to get to velocity is basically, since this is telling you the position for a given timestamp, what you can do then is you can, again, take your final position, take your initial position, and divide it by the total time for that given position. So for instance, if I was to ask you what the velocity is for the entire race, you can say that the runner ran for 400 meters. So 400 meters minus the initial position, which was 0 meters, divided by the time it, or the total time, which was 55 minus 0 seconds. So that's going to give you 400 by 55, and that's the velocity for the entire race. Now, if I were to ask you, well, what was the velocity of the runner between, let's say, position 5 and position 2, um, then you can talk about this position, or this position that the runner had covered. Let's go back a slide here. So let's go back a slide and go to this table. So position 5 and position 2 right here. So you would do xf, that's just 315 minus 135 divided by 44 minus 22. So that's going to be whatever this is going to turn out. But essentially, that's your velocity between that time interval, right? So you can use all that data to cover what the different velocities are depending on the total displacement within the total time that we were talking about, right? And then you can also measure the total velocity at any given position. So you can do not necessarily at 11 seconds or 22 seconds, you can do 10 seconds and 20 seconds based on the equation that we did, because that is equation is going to let you know what the position is for any given time, right, using the trend line. The next part of this was to do with acceleration. Acceleration is another uh, measurement, which is essentially um, the rate of change of velocity over time. And that's basically your final velocity, subtract the initial velocity from it, and divide by the total time it took for that velocity change to occur, right? Um, and that's kind of it for today's lecture, because I want you to focus on these problems. There's a lot of things that depend on these basic concepts. So your distance, displacement, speed, velocity, and acceleration, and the tools that you can use within the spreadsheet. Because the next time when we're going to meet, we're going to use these concepts to essentially determine a lot more things, which are to do with the equations of motion, and we're going to go over a bit of derivation using all these relations. So I want you to spend a lot more time on this, um, on these basic concepts. Uh, if you have to watch the video again, please do so. If you have any questions, again, email me with your questions. I've been trying to respond to your questions as soon as I can. Um, and then there's going to be an exercise handout for you um, to complete and submit by 5 p.m. again, and that's to do with your attendance as well, because we're practicing distance learning. Um, and that's it for today. Thank you very much, and bye bye.